Hi, I'm Alex. Telescopes give us one of the most extraordinary abilities in science. When we observe the universe, we are never seeing it as it is. We are seeing it as it was. In this journey, you'll understand exactly how telescopes do this, why it matters, and how it changed everything we know about the universe. If stories like this spark your curiosity, a gentle subscribe helps this exploration continue and quietly offer more. Now, let's begin. Right this second, you're living in the past. And I'm not joking. Everything you see died before your brain could process it. The person sitting across from you, past. The coffee cup in your hand, past. Your own fingers, also past, even if only by a few billionths of a second. This isn't philosophy. This is physics. And once you understand it, you'll never look at the universe the same way again. Here's the thing that breaks most people's brains. Light doesn't travel instantly. It has a speed 300,000 kilometers per second, 186,000 miles per second if you prefer. That sounds insanely fast. By human standards, a bullet travels about 1 kilometer per second. Light is 300,000 times faster. But here's the cosmic joke. In the scale of the universe, light is slow as hell. It's like watching a turtle cross a highway that stretches across galaxies. Let me give you examples that'll make your head spin. The moon you're looking at right now, that's the moon from 1.3 seconds ago. The light left its surface, traveled through space, entered your eye, and your brain constructed an image. By the time you see it, 1.3 seconds have passed. You're watching a replay, the sun beaming down on you. Right now, that's the sun from 8 minutes ago. If the sun suddenly switched off this very second, just disappeared, you'd have 8 minutes to take selfies in sunlight before everything went dark. You'd be basking in the rays of a dead star and not even know it. Sirius, the brightest star in the night sky. When you look at it tonight, you're seeing light that left in 2016. If you're reading this in 2025, that photon began its journey when Pokemon Go was still a thing, and everyone thought 2016 was a weird year. That photon has been traveling through empty space while you went through 9 years of your life. The universe is playing the cruelest practical joke on you. It lets you think you're living in the present, but you're actually watching reruns. Even your own nose in front of your face is a video clip from the past, just an incredibly recent one. Think about it this way. If someone on the moon waved at you right now, you'd see that wave 1.3 seconds after it happened. They'd already be lowering their arm while you're just noticing them lift it. A video call with someone on the moon, you'd have a 2.6 second delay round trip. Every sentence would feel like talking to someone with terrible internet connection. Video call with aliens on another planet. Forget it. That would be the worst ping of your life. If they're on a planet orbiting Sirius, every hello takes 8.6 years to arrive. By the time they respond, you'd have a college degree or be dead. Now here's where this story gets wild. In 1609, a guy named Galileo Galilei pointed a crude telescope at the night sky. He had no idea what he was about to discover. He built this telescope himself, basically some lenses in a tube, nothing fancy. The magnification was terrible by modern standards, but it was enough. He pointed it at the moon. He saw mountains, craters. The moon wasn't a perfect sphere like everyone thought. It was a world. He pointed it at the sun. He saw spots, dark blemishes on the supposedly perfect celestial body. He pointed it at Jupiter. he saw moons, 4 of them orbiting Jupiter like a miniature solar system. He pointed it at the Milky Way. What looked like a cloudy band to the naked eye exploded into thousands upon thousands of individual stars. Galileo's observations revolutionized astronomy. He proved the Earth wasn't the center of everything. He showed the heavens weren't perfect and unchanging. But here's what Galileo didn't realize. Every single photon entering his telescope was a messenger from the past. He was time traveling and didn't even know it. When he looked at Jupiter's moons, he wasn't seeing them as they were at that moment. He was seeing them from 35 to 50 minutes earlier, depending on where Earth and Jupiter were in their orbits. Every observation was historical documentation, frozen in light. Galileo opened a door to something far stranger than he imagined. He became the first human to use a telescope as a time machine. But let's bring this back down to Earth. Literally, in the room you're sitting in right now, everything you see has a delay. Light from the lamp across the room takes about 10 nanoseconds to reach your eyes. That's 10 billionths of a second. Your brain can't perceive that delay, but it exists. When you're driving at night and your headlights illuminate the road 100 meters ahead, you're seeing that stretch of road from 0.033 seconds ago. The light had to travel there and bounce back to your eyes. When you look at yourself in a mirror, you're not seeing yourself now. You're seeing yourself from a few nanoseconds ago. If the mirror is 1 meter away, the light takes about 6.7 nanoseconds to make the round trip. You're looking at your own past self. A very recent past, sure, but still the past. This leads to a philosophical mind bender. The present doesn't exist in observation. There's only near past and far past. The universe doesn't have a universal now that everyone experiences simultaneously. Every observation is delayed by the speed of light. Reality is always a replay. Now let's scale this up. Way up. If the moon is 1.3 seconds in the past, and the sun is 8 minutes in the past, then Andromeda, the closest large galaxy to our Milky Way, is 2.5 million years in the past. When you look at Andromeda tonight, you're watching a movie from when your ancestors had just split from chimpanzees and started bashing rocks together in East Africa. You're seeing a galaxy as it was when Homo habilis was figuring out stone tools. Some of the stars in that galaxy have died since then. New ones have been born. The spiral arms have rotated slightly. Entire stellar generations have come and gone. But you're seeing none of that. You're seeing the ancient version preserved in light that's been traveling for 2.5 million years just to hit your eyeball. This is real. This is how telescopes work. Every telescope ever built, from Galileo's crude tube to the most advanced space observatories, is a time machine. They don't show you the universe as it is. They show you the universe as it was. But how did we figure this out? How did humanity discover that light has a speed, that observation takes time, that we're all living in an eternal replay? The answer starts with a Danish guy in 1676 who became obsessed with the moons of Jupiter. He noticed something weird, something that didn't make sense. The moons kept lying about when they should disappear behind Jupiter, and that observation changed everything. Copenhagen, Denmark, 1676. Ola Rømer had what most people would call a boring job. He sat at his telescope, night after night, watching one of Jupiter's moons, a little rock called Io, disappear behind the giant planet. eclipse after eclipse after eclipse. He'd record the exact time Io vanished, then wait for it to reappear on the other side. This was precision work, tedious work, the kind of work that makes your eyes hurt and your back ache. But Romer was meticulous. He logged every observation. He built up data over months, then years. And then something weird started happening. The numbers weren't adding up. When Earth was closest to Jupiter in its orbit, Io's eclipses happened earlier than predicted. Not by a little bit, by minutes. When Earth was farthest from Jupiter, the eclipses happened later than predicted, again by minutes. The discrepancy accumulated. Over 6 months, the difference could be 22 minutes or more. His fellow astronomers had a simple explanation: Ole, your clock is broken. But Romer's clock wasn't broken. He checked it obsessively. He compared it against other instruments. The clock was fine. Something else was going on. Then it hit him. The kind of insight that changes everything. It's not my clock, Romer said. It's the light. Light is slow. Here was his razor-sharp logic. When Earth moves farther from Jupiter, light from Io has to travel a greater distance to reach us. Greater distance means more time. The delay in the eclipse wasn't Io being late. It was light taking longer to cross the extra space. When Earth was closer to Jupiter, light had less distance to cover. The eclipses appeared to happen early because the light arrived sooner. The delay itself was proof that light has a finite speed. Romer calculated that light took approximately 22 minutes to cross the diameter of Earth's orbit around the Sun. His number was off. He didn't know the exact size of Earth's orbit yet, but the principle was absolutely correct. Light travels. It takes time. Observation isn't instantaneous. Imagine Romer presenting this at a scientific conference. Romer, gentleman, light is slow. His colleagues, Ole, how much aquavit have you been drinking? But he was right, and this discovery was about to demolish every assumption humanity had about reality. Before Romer, the prevailing belief was simple: light is instantaneous. When you look at something, you see it as it is right now. Observation happens in real time. After Romer, everything changed. Observation does not equal real time. Everything we see is delayed. Every photon is a letter from the past. Astronomy wasn't just the study of space anymore. It became the study of history. Let's dig into the details of what Romer actually did, because this experiment is more fascinating than most people realize. Over 2 years, Romer observed 140 eclipses of Io. That's 140 nights of sitting in the cold eye pressed to a telescope, recording times down to the second. The accumulated timing difference over 6 months was roughly 22 minutes. But here's the kicker. Earth's orbit isn't a perfect circle. It's an ellipse. That meant Romer had to account for Earth's varying distance from Jupiter throughout the year. The math got complicated fast. Think of it like this. Imagine you're playing an online game. You press a button to shoot, but you're playing on a server thousands of miles away. There's a delay, what gamers call ping or lag, between when you press the button and when the server registers the action. That delay is caused by the signal having to travel from your computer across cables and routers to the server and back. A ping of 50 milliseconds means the server is roughly 7,500 kilometers away. Light and electrical signals in fiber optic cables travel at nearly the speed of light, so distance equals delay. Now scale that up. If you're playing a game with someone on the moon, your ping would be 2,600 milliseconds, 2.6 seconds round trip. Every time you move, there's a 2.6-second delay before they see it, and another 2.6 seconds before you see their response. Frustrating, but playable. Playing a first-person shooter with an alien on Andromeda ping, 2.5 million years. Totally unplayable. You fire a shot, wait 2.5 million years for them to see it, then wait another 2.5 million years to see if you hit. By then, their entire civilization might be extinct. Rømer's discovery had implications far beyond astronomy. Centuries later, Einstein would use this concept as a foundation for his theory of relativity. The idea that light has a finite speed, that information can't travel instantaneously, is baked into the structure of space-time itself. GPS satellites orbiting Earth have to account for light speed delays down to the nanosecond. If they didn't, your navigation would be off by miles. Every telecommunications system on the planet, fiber optic, cables, satellite links, wireless networks, operates on principles that trace back to what Rømer figured out while watching a moon disappear behind Jupiter. So here's what we know now. Light needs time to travel. It's not instant. It's fast, but it's not infinite. And if we had tools powerful enough to catch photons from extremely far away, billions of light years away, we could see the universe as it was billions of years ago. But you can't do that with Galileo's crude telescope. You need something far more advanced. You need a weapon of cutting-edge technology, a machine with a mirror bigger than your house, colder than outer space, and more precise than brain surgery. And it works in ways you won't believe. Alright, this section is about technology, but don't worry, I'm not going to turn you into a NASA engineer. I'm just going to give you enough badass facts that you can casually drop into conversations. Yeah, I know Webb operates at negative 233 degrees Celsius. What about it? That's it. Let's go. The brutal principle is simple size equals power. The bigger the mirror or lens, the more photons you catch. More photons mean you can see fainter objects. Fainter objects are usually farther away. Farther away means looking deeper into the past. Here's the math that blows people's minds. If you double the diameter of a telescope's mirror, you don't double the light gathering power, you quadruple it. A 4-meter mirror collects 4 times as much light as a 2-meter mirror. Not twice, 4 times. Light gathering power increases with the square of the diameter. This means if you want to see twice as deep into the past, you need a mirror 4 times larger. Want to see twice as deep? Again, 16 times larger. The race to build giant mirrors becomes an engineering nightmare very quickly. Which brings us to problem number 1. Gravity is the enemy. Glass flows like honey if you make it too big. It sounds insane, but it's true. Glass is technically a supercooled liquid. Over time, it sags under its own weight. For telescope mirrors, this happens fast. The practical limit for a single solid mirror is about 8 meters across. Go bigger than that, and the mirror warps under its own mass. It sags in the middle. The focus point shifts. The image goes blurry. Useless. It's like holding a giant pizza on 2 hands. No matter how carefully you hold it, the middle droops. Problem number 2. Temperature is a demon. Daytime gets hot. The mirror expands. Nighttime gets cold. The mirror contracts. A temperature shift of just a few degrees Celsius can cause the mirror to expand or contract by millimeters. That shifts the focal point. Your image of a galaxy 10 billion light years away goes blurry because it got 2 degrees warmer outside. Disaster. So how do you build a mirror bigger than 8 meters without it collapsing under its own weight or warping with temperature changes? The genius solution: segmented mirrors. Instead of one giant mirror, you build dozens or hundreds of small hexagonal segments. Each segment is individually controlled by motors and computers. They work together, forming a single unified optical surface. It's like a honeycomb made of mirrors all perfectly aligned. Let's look at 2 case studies. Case study 1, James Webb Space Telescope. Webb's specs are insane. 18 hexagonal segments made of beryllium. Each segment is 3 meters across, about the size of a door. Combined, they form a 6.5 meter primary mirror. Each segment is coated with a layer of gold, 100 nanometers thick, about 1,000th the width of a human hair. Gold reflects infrared light better than any other material. The precision required is terrifying. Each segment has to be aligned to within 1/10,000th the width of a human hair. If they're off by even that tiny amount, the images blur. To maintain this precision, Webb uses 126 tiny motors that constantly adjust the segments during observations. They tweak the alignment in real time, compensating for temperature shifts and vibrations. Then there's the sun shield. This thing is the size of a tennis court. 5 layers of material thinner than a garbage bag, but capable of blocking 200,000 times the heat of the sun. It keeps the mirror at -233 degrees Celsius, about 40 degrees above absolute zero. At that temperature, Webb can detect the faint infrared glow of galaxies over 13.5 billion light-years away. Case study 2, extremely large. Telescope ELT, currently under construction in Chile. The ELT is a monster, 798 hexagonal segments. The primary mirror is 39 meters across, bigger than a tennis court. When completed, it'll collect 15 times more light than any current optical telescope. The challenges are insane. Each segment has to be aligned to nanometer precision. And because it's on the ground, wind temperature changes, and the telescope's tilt as it tracks objects across the sky all affect the mirror shape. So the system adjusts the segments thousands of times per second. Active optics in real time. The mirror literally shapeshifts to stay perfectly focused, to give you a sense of the precision involved. If Webb's mirror were scaled up to the size of the United States from coast to coast, the allowable error would be 2.5 centimeters. That means you couldn't misplace a grain of sand on a map of California. That's NASA-level perfectionism. Now let's talk about real magic adaptive optics. The problem: Earth's atmosphere acts like a rippling curtain of water. It bends light in random directions. This is why stars twinkle. They're not actually twinkling, they're perfectly steady. But our atmosphere is turbulent, and that turbulence makes the light wiggle around. The solution sounds like science fiction. You fire a laser into the atmosphere, creating an artificial guide star about 90 kilometers up. Then you watch how the atmosphere distorts that fake star. A deformable mirror in the telescope adjusts its shape in the opposite direction, canceling out the distortion. This happens more than 1,000 times per second. The result: ground-based telescopes can achieve sharpness rivaling space telescopes, even though they're looking through a turbulent atmosphere. The Keck Observatory in Hawaii has 2 10-meter telescopes equipped with adaptive optics. They can see details on stars hundreds of light years away, as if the atmosphere didn't exist. Now, let's talk about detectors the photon traps. Human eyes capture about 1% of the photons that hit them. Photographic plates, used in the 1800s and 1900s, also about 1%. Modern electronic detectors, over 90%. Here's how they work. A single photon strikes the detector and liberates a single electron. That electron is counted and recorded. A photon that's been traveling for 10 billion years, crossing the entire observable universe, gets caught and counted. The miracle is an accumulation. Telescopes expose their detectors for hours, sometimes days. Millions of photons from a distant galaxy slowly build up into an image. Each photon is a pixel. Each pixel is a piece of history. But here's a question. Why does Webb have to be so cold? Everything warm emits infrared radiation. If your telescope is warmer than the object you're trying to observe, you'll just see your own heat glow. It's like wearing night vision goggles. Inside a bright room, useless. Webb operates at negative 233 degrees Celsius. That's colder than outer space in some regions. Space itself is about 3 Kelvin on average, but the sun heats things up. Webb hides behind its enormous sun shield to stay cold. Earlier, infrared telescopes like Spitzer used liquid helium to cool their instruments. When Spitzer ran out of helium after 5 years, it could no longer observe at the longest infrared wavelengths. Think of Webb as a night hunter sitting in a freezer set to death by cold. If you're warmer than your prey, you'll just see yourself glowing like a flashlight in a dark theater. The colder the telescope, the less thermal noise. Webb can detect galaxies 1,000,000 times fainter than Hubble. It can hear photons from 13.5 billion years ago. So here's the full technology stack. Giant mirror collects massive amounts of photons. Segmented precision focuses perfectly. Adaptive optics cancels atmospheric distortion. Extreme cold eliminates thermal noise. 90% plus detectors catches every photon. Spectroscopy breaks light into its signature wavelengths. Put it all together, and you have the perfect time machine. The weapon is ready. A mirror bigger than a house. Cold as hell, precise as surgery. But the journey of a photon to reach us isn't a straight line. Light has to survive an odyssey across the cosmos. Every photon from a galaxy 10 billion light years away has to survive the expanding universe, stretching it like taffy. Cosmic dust trying to scatter it away. Supermassive black holes warping space-time around it. And if it's lucky, extremely lucky, after 10 billion years, it slams into our detector. That journey is an epic in itself. Year zero, deep in the core of a star in a galaxy 13 billion light years away. Nuclear fusion is raging. Hydrogen atoms slam together under unimaginable pressure and heat. They fuse into helium, and in that moment of fusion, a single photon is born. This photon begins the longest journey of its existence. Its destination, Earth, a planet that doesn't exist yet, a world that won't form for another 9 billion years. The stakes survive, cross the universe, tell the story of the early cosmos. This photon has superpowers that make it the perfect messenger. It has no rest mass, so it travels at the speed of light, the cosmic speed limit. It doesn't decay over time like radioactive particles. It maintains its energy and direction unless something interferes with it. The miracle a photon from 13 billion years ago arrives at your telescope essentially intact. It's the same photon that left that ancient star carrying the same information. This is why astronomy exists. This is why we can study the past, because photons are immortal messengers. But the journey isn't easy. To reach us, this photon has to survive 4 major obstacles. Obstacle number 1, the expanding universe, the space stretcher. As the photon travels, the universe itself is expanding. Space between galaxies is stretching like dough being pulled. The photon is riding on that space. As space expands, the photon's wavelength gets stretched too. This is redshift. Light that started as blue or violet gets stretched to red, then to infrared. The photon carries a timestamp in its wavelength. The more stretched it is, the farther it traveled, the older it is. Astronomers measure this through spectroscopy. They split light into its component colors and look for the chemical signatures: hydrogen, oxygen, carbon. Every element leaves specific lines in the spectrum. If those lines are shifted toward the red end, you know the light has been stretched by cosmic expansion. Here's how it works in practice. A redshift of z equals 1 means the galaxy is about 8 billion light years away. We're seeing it from 8 billion years ago. A redshift of z equals 6 means about 13 billion light years. We're seeing the universe when it was less than 1 billion years old. A redshift of z equals 13. That's what Webb just found. Galaxies from 13.5 billion years ago, just a few 100 million years after the Big Bang. Let's get specific about expansion. The universe expands at roughly 70 kilometers per second for every megaparsec of distance. A megaparsec is 3.26 million light years. So, a galaxy 1,000 megaparsecs away is receding from us at 70,000 kilometers per second. But here's the key. The galaxy isn't moving through space. Space itself is expanding. Imagine drawing 2 dots on a balloon, then inflating it. The dots move apart, but they're not traveling across the balloon's surface. The surface itself is stretching. Our photon is riding that expanding surface, getting stretched along with it. Obstacle number 2, cosmic dust, the light saboteur. Between the stars, space isn't empty. It's filled with dust. Tiny grains of silica, carbon iron smaller than smoke particles. Individually, they're nothing. But there are trillions of them, scattered across vast distances. And they mess with light. This causes reddening. Blue light has a shorter wavelength, so it scatters more easily when it hits dust particles. Red light has a longer wavelength and passes through more easily. The result: distant objects look redder than they actually are. It's the same principle behind why Earth's sky is blue during the day and red at sunset. During the day, blue light scatters in all directions, filling the sky. At sunset, sunlight travels through more atmosphere, and the blue scatters away, leaving red. That's Rayleigh scattering. The solution: observe at multiple wavelengths. Look at the same object in ultraviolet visible light and infrared simultaneously. Infrared passes through to dust much more easily than visible light. By comparing wavelengths, astronomers can calculate the object's true color and brightness. This is why Webb specializes in infrared. It can see through dust like an X-ray sees through skin. Consider the center of the Milky Way. In visible light, it's completely obscured by dust. You can't see anything. But switch to infrared, and suddenly you can see Sagittarius A star, the supermassive black hole at the galaxy's core. Or look at star-forming regions. Dense clouds of gas and dust collapse to form new stars. In visible light, you see the cloud's outer surface. Switch to infrared or radio, and you see inside protostars forming hidden from optical view. The Orion Nebula is a perfect example. Optical telescopes show the glowing gas on the surface. Infrared telescopes, like Spitzer and Webb, reveal the dense cores inside where stars are being born. Obstacle number 3, gravitational lensing, the universe's free telescope. Einstein predicted this in 1915. Mass warps space-time. Light travels through space-time. Therefore, mass bends light. A massive object like a galaxy cluster acts as a lens. Light from a more distant galaxy behind it gets bent around the cluster. This creates arcs, multiple images, or even complete rings called Einstein rings. This has a dual effect. The bad images get distorted and hard to analyze. The good, natural magnification. It's a free telescope provided by the universe itself. Some galaxies Webb has detected were only visible because gravitational lensing magnified them by 10 to 50 times. Without the lens, they'd be too faint to see. Gravitational lensing also lets us map dark matter. Dark matter doesn't emit light, but it has mass. It bends light just like normal matter. By analyzing how light is distorted around galaxy clusters, astronomers calculate the cluster's total mass, including the dark matter. Hubble and Webb have photographed hundreds of clusters with strong lensing. Each one reveals the distribution of invisible dark matter. There are different types of lensing. Weak lensing causes slight distortions you can only detect statistically by analyzing thousands of galaxies. Strong lensing creates obvious arcs and multiple images. Microlensing happens when a single star magnifies a more distant star behind it. There's even a time delay effect. Light traveling different paths around a gravitational lens arrives at different times. By measuring this delay, astronomers can calculate the universe's expansion rate. Different paths, different arrival times, same source. Obstacle number 4, Earth's atmosphere, the final boss for ground telescopes. If you are observing from Earth's surface, the atmosphere is your enemy. Turbulent air makes stars twinkle. It blurs images, limiting resolution to about 1 arcsecond, much worse than what the telescope's optics are capable of. Water vapor absorbs infrared light. Ozone absorbs ultraviolet. Certain wavelengths simply cannot be observed from the ground. And then there's light pollution. City lights illuminate the sky, making it harder to see faint objects. This is why major observatories are built on remote mountaintops or in deserts far from civilization. Space telescopes avoid all this. Hubble orbits at 550 kilometers. Webb sits at the L2 Lagrange, 1.5 million kilometers from Earth. No atmosphere, no light pollution, no water vapor. They can see far deeper into the past than any ground-based telescope. The journey timeline. 1 photon's 10 billion year trip. Let's follow a single photon from a galaxy 10 billion light years away. Year 0. The photon is born in a young star. The universe is at cosmic noon, the peak of star formation. The photon leaves the star's surface heading into the void. 2 billion years in, it passes through a dust cloud in its home galaxy. It gets scattered slightly. Its wavelength shifts from blue toward red. 5 billion years in, it encounters a massive galaxy cluster. Gravitational lensing bends its path. Luckily, it doesn't slam into another star. 8 billion years in cosmic expansion accelerates. Redshift accumulates. The photon stretches from visible light into infrared. 10 billion years in today, the photon races toward the L2 point. It passes through Webb's enormous sunshield. It reflects off all 18 hexagonal mirror segments. It slams into the detector. It liberates a single electron. That electron is counted and recorded. Mission accomplished. The information the photon carries, a letter from the past. Every photon carries encoded information about its source and journey. About the star chemical composition shows up as spectral lines. Surface temperature is revealed by the energy distribution. Atmospheric pressure affects the width of spectral lines. Velocity shows up as Doppler shift. About the journey, reddening tells us what dust it passed through. Distortion reveals gravitational lensing. Redshift equals distance equals time. It's like Sherlock Holmes in space. The photon is a witness. Spectroscopy is the interrogation. Decode the information, and you reconstruct a crime scene from 10 billion years ago. If we could interview a photon after its 10 billion year journey, here's how it might go. Question: what did you see on the way? Photon: dust. So much dust. And a black hole nearly swallowed me. Question: are you tired? Photon: I travel at the speed of light. Time doesn't exist for me. From my perspective, the journey was instantaneous. Mind blown. The photon survived. It crossed 10 billion years and trillions upon trillions of kilometers. Now, it sits in NASA's hard drives, waiting to be decoded. But before we look that far back, let's start closer to home, our neighborhood within 1,000 light years, where every star you see is a historical snapshot from the Middle Ages, from Roman times, from the age of pyramids, and one of them might already be dead, and we don't know it yet. Welcome to our neighborhood. Within 1,000 light years of Earth, there are roughly 100,000 stars. Every single one you observe is a snapshot from years, decades, or centuries ago. Close by cosmic standards, impossibly far by human standards. Let's meet the neighbors. Star number 1, Sirius, the diamond of the night sky. Sirius is the brightest star in the night sky, excluding the sun. It sits 8.6 light years away. When you look at Sirius tonight, you're seeing it as it was in 2016, assuming you're observing in 2025. But Sirius has a secret. It's a binary system. Sirius A is the main star twice the mass of the sun, blue-white blazing bright. Sirius B is a white dwarf, the collapsed core of a dead star. Here's the mind-blowing fact. Sirius B is the size of Earth, but has the mass of the sun. 1 teaspoon of Sirius B weighs about 1 ton. The discovery of Sirius B happened in 1862. Alvin Graham Clark was testing a new telescope. He aimed it at Sirius. Next to the brilliant main star, he saw a faint dot. That was Sirius B, previously hidden by Sirius A's overwhelming glare. Sirius has cultural significance across civilizations. The ancient Egyptians called it Sopdet. When Sirius rose just before dawn, it signaled that the Nile's annual flooding was coming. The phrase, dog days of summer, comes from Sirius, the dog star. Sirius B is a laboratory for extreme physics. Surface gravity is 350,000 times stronger than Earth's. If you could stand on Sirius B, assuming it had a solid surface, you'd weigh 350,000 times your normal weight. A 70-kilogram person would weigh 24,500 tons. Sirius B is cooling slowly over billions of years. Eventually, it will become a black dwarf, a completely dead star. But the universe isn't old enough yet for any black dwarfs to exist. Star number 2, Betelgeuse, the ticking time bomb in Orion. Betelgeuse is a red supergiant in the constellation Orion. You can see it with the naked eye, the reddish-orange dot marking Orion's shoulder. It's 642 light-years away. When you look at it tonight, you're seeing it as it was around the year 1383. The size is insane. If you replace the Sun with Betelgeuse, its surface would extend beyond Jupiter's orbit. Its diameter is roughly 1,000 times the Sun's. Its mass is 15 to 20 times the Sun's. Here's the dramatic twist. Betelgeuse is going to explode. Soon. Well, soon, on cosmic timescales, within the next 100,000 years. When it explodes, it will shine as bright as the full moon. You'll see it during the day, for weeks. But here's the problem. Has it already exploded? Light takes 642 years to reach us. If Betelgeuse exploded in the year 1400, we'd see it in 2042. We're watching a replay from 642 years ago. The star might already be gone, and we're staring at its ghost. Hubble has resolved Betelgeuse's surface. It shows bright spots and dark regions. The star is breathing, expanding, and contracting unevenly. There's a nebula around it, gas blown away by stellar winds. In late 2019, Betelgeuse dimmed by 60%. Astronomers panicked. Is it about to explode? Media went crazy. Nearby supernova incoming. The truth. Betelgeuse had ejected a massive dust cloud that temporarily blocked its light. Hubble captured images of the dust cloud. It covered a quarter of the star's surface. By 2020, Betelgeuse brightened back to normal. False alarm, but a reminder, it will explode. Eventually. Star number 3, Arcturus. The migrating giant, Arcturus, sits 37 light-years away. If you observe it in 2025, you're seeing light from 1988, the year the Berlin Wall was still standing. It's the 4th brightest star in the night sky. Arcturus is a red giant nearing the end of its life. Its diameter is roughly 26 times the Sun's. It's burning helium into carbon in its core. In about 1 million years, it will shed its outer layers, forming a planetary nebula, leaving behind a white dwarf. But Arcturus is special. It's a high-velocity star racing through the Milky Way at 120 kilometers per second. It doesn't belong to the young stellar population around us. It might be an immigrant from a dwarf galaxy the Milky Way consumed long ago. The Crab Nebula, a crime scene. 1,000 years old, in 1054, Chinese astronomers recorded a guest star appearing in the sky. It was bright enough to see during the day for 23 days, visible at night for 653 days. Then it faded. The Crab Nebula sits 6,500 light-years away. The explosion actually happened around 446 BCE during the Neolithic period, but the light took 6,500 years to reach Earth, so Chinese observers saw it in 1054. Hubble reveals an expanding shell of gas moving at thousands of kilometers per second. Complex filaments, where the blast wave collides with interstellar gas. At the center, a pulsar, a neutron star, spinning 30 times per second. The pulsar is the collapsed core of the exploded star. It's about 20 kilometers across, but contains 1.4 times the Sun's mass. 1 teaspoon of neutron star material weighs 1 billion tons. It spins 30 times per second, emitting radio pulses with incredible precision. By measuring those pulses over years, astronomers have detected that it's slowing down losing energy. Different telescopes see different aspects. Chandra's X-ray view shows gas heated to millions of degrees. Hubble's optical view shows filaments. Radio telescopes detect synchrotron radiation from electrons spiraling in magnetic fields. Spitzer's infrared view reveals warm dust. Each wavelength is a different perspective on the explosion. Modern technology, Gaia, the 3D map of our galaxy. The European Space Agency's Gaia mission, launched in 2013, it's mapping over 1 billion stars. Position, distance, motion, brightness, color, all measured with insane precision. Gaia can measure positions accurate to 10 microarc seconds. That's like seeing a coin on the moon from Earth. Stars aren't stationary. They orbit the galaxy's center. One orbit takes 200 to 250 million years. The Sun has completed about 20 orbits since it formed. Gaia tracks these stellar streams, revealing the Milky Way's structure. Gaia has discovered stellar streams, rivers of stars that are the remnants of dwarf galaxies the Milky Way devoured. High-velocity stars ejected from the galaxy's core. Tens of thousands of previously unknown binary stars. Even exoplanets detected through the wobble they cause in their host stars. Variable stars, cosmic lighthouses, Cepheid, variables pulsate regularly. Henrietta Leavitt discovered in 1912 that their pulsation period is directly related to their true luminosity. Longer period equals brighter star. Measure the period, and you know the star's true brightness. Compare that to its apparent brightness, and you calculate distance. Hubble used Cepheids to prove the universe is expanding. Our Lyrae stars are common in globular clusters. They pulsate over hours. Mira variables are dying red giants that vary over months, sometimes by factors of dozens in brightness. Mira itself has been observed for over 400 years, the longest baseline of any variable star. These long observational baselines are critical. Delta Cephei E has been monitored since the late 1700s. Mira since 1596. You need decades or centuries to see slow changes. Comparing old and new observations reveals stellar evolution in action. Brown dwarfs, failed stars. Brown dwarfs are too small to fuse hydrogen, less than 0.08 solar masses. They're between stars and planets. They glow faintly from leftover heat. Hundreds have been found within a few dozen light years. They're hard to detect because they're so dim. Infrared telescopes see them more easily. They represent the minimum mass threshold for becoming a star. They're the transition between stars and planets. Some even have weather clouds and winds like gas giant planets. These stars, miraculous as they are just our close neighbors. They show us the past from years to centuries ago. But if you want to look deep into the past, if you want to see the universe when it was young, you have to look farther. Millions of light years, billions of light years. Andromeda, our nearest large neighbor, is 2.5 million light years away. When you look at it tonight, you're watching it from when early human ancestors had just started using stone tools. Some stars in it have died, others have been born. The spiral arms have rotated slightly, and if you look even farther, hundreds of millions of light years out galaxies are colliding, merging, destroying each other. Billions of light years away is cosmic noon, the golden age of the universe. At 13 billion light years, the first galaxies are just forming, and Webb is breaking every record, pushing the limits farther than ever before. When you look up at the night sky on a clear moonless night away from city lights, you might spot a faint, fuzzy patch in the constellation Andromeda. To the naked eye, it's unremarkable, just a dim smudge among thousands of stars. But that smudge is something extraordinary. It's the Andromeda Galaxy, our nearest large galactic neighbor, sitting 2.5 million light years away. Let that sink in for a moment. 2.5 million light years. Every photon from Andromeda that enters your eye tonight has been traveling through space since long before humans existed in any form we'd recognize. When that light left Andromeda, our ancestors, Australopithecus, were just beginning to walk upright across the African savanna. They were barely using stone tools. They had no language, no art, no conception that they were looking at anything beyond pretty lights in the sky. And here's the thing that makes this even more mind-bending. Andromeda isn't just a distant object we're observing. It's a massive spiral galaxy containing roughly 1 trillion stars. 1 trillion. That's about twice as many stars as our own Milky Way. Each one of those stars has its own story, its own life cycle, and potentially its own planets. The Hubble Space Telescope has done something remarkable with Andromeda. It's resolved individual stars within the galaxy. Think about what that means. We're not just seeing Andromeda as a blob of light. We're picking out individual suns 2.5 million light years away and studying them one by one. Each photon from each star carries information about conditions in Andromeda, from when early human ancestors were learning to use fire. Some of those stars we observe in Andromeda today have already died. They went supernova, exploded, collapsed, but the light from their deaths hasn't reached us yet. They're stellar ghosts, appearing alive in our telescopes, while in reality, they've been dead for hundreds of thousands of years. Other stars have been born since the light we're seeing tonight left Andromeda. New stellar nurseries have ignited, planetary systems have formed, and we won't see any of it for another few 100,000 years. The galaxy's spiral arms have rotated slightly since the light we observed departed. Stars have orbited Andromeda's center, some completing multiple revolutions in the 2.5 million years it took their light to reach us. The supermassive black hole at Andromeda's core has consumed countless stars and clouds of gas. All of this happened, and we're completely blind to it because we're watching a replay from deep antiquity. Hubble's observations revealed something else fascinating. Andromeda appears to have consumed several smaller galaxies in its past. We can see stellar streams, rivers of stars, that are the shredded remains of dwarf galaxies that wandered too close to Andromeda and were torn apart by tidal forces. These streams are visible today, wrapping around Andromeda like gossamer threads, telling us about violent mergers that occurred hundreds of millions of years ago, but which we're only seeing evidence of now because the light took so long to arrive. But here's where this story takes a dramatic turn. Andromeda isn't just sitting there in space. It's moving, and it's moving toward us at about 110 kilometers per second, or roughly 250,000 miles per hour. That might sound terrifying, but remember, space is vast beyond comprehension. At this speed, Andromeda will collide with the Milky Way in approximately 4 billion years. Let me put that in perspective with an analogy. Imagine two extremely drunk people on opposite ends of a football field, slowly staggering toward each other at a walking pace. The motion is almost imperceptible. It'll take them many minutes to meet. When they finally do collide, it's going to be spectacular. That's Andromeda and the Milky Way. Slow motion disaster written in the stars. Computer simulations show us what this collision will look like. And I should clarify immediately. When galaxies collide, individual stars almost never hit each other. The space between stars is so vast that you could pass two galaxies completely through each other, and the probability of any two stars actually colliding is essentially zero. It's like throwing two swarms of gnats at each other at high speed. The gnats would mostly just intermingle without touching, but the gas clouds within galaxies, that's a different story. When Andromeda and the Milky Way merge, their gas clouds will collide violently. These collisions will compress the gas, triggering massive waves of star formation. Regions that were relatively quiet will suddenly light up with billions of new stars. The night sky viewed from whatever planet might still harbor observers 4 billion years from now will be spectacular beyond imagination, filled with brilliant new stellar nurseries, glowing nebulae, and clusters of hot young stars. The two supermassive black holes at the centers of both galaxies, Sagittarius A in the Milky Way and Andromeda's central black hole, will eventually spiral toward each other and merge, releasing gravitational waves so powerful they'll ripple across the universe. But we won't be around to see it. The Sun will have already expanded into a red giant long before this cosmic dance concludes, likely consuming Earth in the process. For now, Andromeda sits peacefully in the night sky, a time capsule from 2.5 million years ago. Every observation we make captures it as it was, when our ancestors were barely distinguishable from other apes. The stars we see might be long dead. New stars might have formed. The spiral arms might have shifted. And we won't know any of these changes until the light from those events finally completes its multi-million-year journey to our telescopes. This is what makes astronomy fundamentally different from every other science. We're not experimenting in a lab or examining samples we can hold in our hands. We're looking backward through time, using light as our messenger, piecing together histories that unfolded millions or billions of years ago. Andromeda isn't just our nearest galactic neighbor, it's a window into the past, showing us what a massive spiral galaxy looked like in an era when Earth was dominated by creatures that would eventually evolve into us. But here's something worth remembering. As vast and ancient as Andromeda is, as mind-bending as its 2.5 million year time delay, seems it's actually just a baby in cosmic terms. It's practically next door. Because when we look farther out into space, when we push our telescopes to their limits and capture light from galaxies billions of light years away, we start seeing the universe do things that seem absolutely impossible. Galaxies don't just sit peacefully like Andromeda. They collide, they merge, they tear each other apart in slow motion catastrophes that make our future merger with Andromeda look like a gentle waltz. And that's where our story goes next. If you think Andromeda's slow motion approach toward the Milky Way sounds dramatic, wait until you see what happens when galaxies have already started colliding. About 45 million light years away in the constellation Corvus, there's a system called the antennae galaxies. When you look at images of the antennae, you're seeing a snapshot from 45 million years ago, from when Earth was in the Eocene epoch. Early primates were just evolving, and the dinosaurs had been extinct for only 20 million years. What you see in those images is absolute chaos. Two spiral galaxies, NGC 4038 and NGC 4039, are locked in a gravitational embrace, tearing each other apart. Long tidal tales of stars and gas stream away from both galaxies, stretching hundreds of thousands of light years into space. These tails are where the galaxies get their name. They look like the antennae of an insect reaching out into the cosmic void. But here's what's important to understand about galactic collisions, because it's deeply counterintuitive. When two galaxies collide, the individual stars within them almost never actually hit each other. Remember, stars are separated by vast distances, light years of mostly empty space. The probability of any two stars directly colliding during a galactic merger is essentially zero. If you were standing on a planet in one of these colliding galaxies, watching the night sky, you'd see the overall shape of your galaxy change over millions of years. But individual stars would pass by harmlessly, separated by distances so vast they'd never interact. Think of it like this: if galaxies were two clouds slowly drifting through each other, the water droplets making up those clouds would mostly pass by without touching. That's how sparse galaxies are. But, and this is crucial, while stars don't collide, gas clouds absolutely do. Galaxies contain enormous amounts of gas between their stars. When two galaxies merge, these gas clouds smash into each other at speeds of hundreds of kilometers per second. The collisions are violent, compressing the gas to tremendous densities. And compressed gas does something spectacular. It collapses under its own gravity and forms new stars. Lots of new stars, thousands, millions. Entire stellar nurseries ignite across the collision zone, lighting up like cosmic fireworks. This process is called a starburst, a period of incredibly rapid star formation triggered by the collision. In the antennae galaxies, telescopes have detected over 1,000 young bright star clusters. These aren't individual stars. They're clusters containing thousands of stars, each all born in the chaos of the collision. The rate of star formation in the antennae is many times higher than in quiet galaxies like the Milky Way. Different telescopes reveal different aspects of this cosmic violence. Optical telescopes like Hubble show the bright blue regions where massive young stars are forming. Infrared telescopes peer through the dust clouds and reveal hidden stellar nurseries invisible to optical light. X-ray telescopes detect the aftermath, extremely hot gas heated to millions of degrees by supernova explosions and stellar winds. Radio telescopes map the neutral hydrogen gas being torn from both galaxies and flung into intergalactic space. Each wavelength is like a different sense, sight, hearing, touch, all combining to give us a complete picture of what's happening in this 45 million year old collision that we're only seeing now. Another spectacular example is Messier 82, often called the Cigar Galaxy, about 12 million light years away. M82 is undergoing a starburst, forming stars at roughly 10 times the rate of the Milky Way. Something gravitationally disturbed this galaxy, likely a close encounter with its larger neighbor M81, and triggered this explosive period of star formation. When you observe M82 with an X-ray telescope like Chandra, you see something extraordinary. Hot gas is being blown out of the galaxy in a massive galactic wind perpendicular to the galactic disk, creating huge lobes extending thousands of light years into space. These winds are driven by the combined force of supernova explosions and stellar winds from thousands of massive hot young stars. The energy involved is staggering, equivalent to billions of supernova explosions. What we're seeing in M82 happened 12 million years ago when early apes were beginning to evolve on Earth. The starburst might have already ended, the galactic winds might have dissipated, or the process might still be ramping up. We won't know until the light from those more recent events finally reaches us millions of years from now. Computer simulations help us understand these collisions in ways direct observation cannot. We can't watch a galactic merger happen in real time. They unfold over hundreds of millions of years. But we can simulate them. Astrophysicists program supercomputers with the laws of physics, gravity gas dynamics, star formation, and then crash virtual galaxies into each other at various speeds and angles. These simulations reveal the full timeline of a collision. First approach takes tens of millions of years, with the galaxy's gravitational fields beginning to distort each other. First pass-through creates tidal tails. Stars and gas are flung outward by tidal forces. The galaxies swing back around their gravity, binding them together. Second collision is more violent, triggering intense star formation. Multiple passes occur over hundreds of millions of years, each one more chaotic. Eventually, the two galaxies merge completely their stars, intermixed their gas, consumed in star formation, or blown away in galactic winds, leaving behind a single elliptical galaxy, a cosmic mosh pit that's settled into exhausted calm. And this brings us to our future, when Andromeda and the Milky Way collide in 4 billion years. This is exactly what will happen. Simulations of our future merger show the Sun and its planets being flung into different orbits, possibly ejected into intergalactic space entirely. The night sky, as seen from Earth, if Earth still exists, will be unrecognizable. Stars from both galaxies will be scattered into new configurations. The combined galaxy, which astronomers have playfully nicknamed Milkomeda, will likely be an elliptical rather than a spiral. But here's the beautiful part. While this collision might sound violent and destructive, it's actually how galaxies grow. Nearly every large galaxy we observe shows evidence of past mergers. Stellar streams, warped disks, shells of stars. All these features tell us about ancient collisions. Galaxy formation isn't a smooth process where gas gently collapses into a rotating disk. It's violent, chaotic. Galaxies grow by cannibalizing their neighbors, consuming smaller galaxies and merging with equals. You could think of galactic collisions like two clouds passing through each other, but clouds made of fire birthing billions of new stars in the process. It's the universe's way of recycling and renewal playing out over timescales so vast that human civilization is barely a blink in comparison. The antennae galaxies, M82, and thousands of other colliding systems visible in our telescopes are all showing us events from millions of years in the past. Some of these collisions might have already resolved into peaceful, merged galaxies, but we won't see that outcome for millions of years. We're watching cosmic history unfold in slow motion, frame by frame, with each frame separated by millions of years. And while collisions trigger spectacular bursts of star formation, there was a time when the entire universe was forming stars at an incredible rate, even without collisions. A time when galaxies were generally smaller, but far more active, when supermassive black holes were feeding voraciously, when the universe was at its most productive. That era has a name, cosmic noon, and it's where our story goes next. Imagine you could stand on a hilltop and watch an entire city's history unfold across centuries. You'd see it grow from a small settlement to a bustling metropolis, reach a peak of activity and construction, and then gradually settle into a more mature, quieter state. The universe has followed a similar arc, and the peak of that arc, the era of maximum cosmic activity, occurred roughly 8 to 12 billion years ago, when the universe was between 2 and 6 billion years old. Astronomers call this era cosmic noon. When telescopes observe galaxies 8 to 12 billion light years away, they're seeing this golden age directly. They're capturing light that left those galaxies when the universe was at its most productive, its most energetic, its most vibrant. And what they see is extraordinary. Galaxies during cosmic noon were forming stars at rates 10 to 100 times higher than galaxies today. The Milky Way currently forms stars at a rate of about 1 to 2 solar masses per year. That is enough gas collapses to create 1 or 2 sun-sized stars annually. During cosmic noon, typical massive galaxies were forming stars at rates of 100 to 1,000 solar masses per year. Some extreme cases reached several thousand solar masses per year. These weren't brief bursts triggered by collisions. This was sustained prolific star formation over hundreds of millions of years. At the same time, supermassive black holes at the centers of galaxies were feeding voraciously. These black holes, containing millions or billions of solar masses, were accreting huge amounts of gas and shining as quasars, the brightest sustained objects in the universe. A single quasar could outshine its entire host galaxy, powered by gas spiraling into the black hole at relativistic speeds, heating to millions of degrees, and emitting across the entire electromagnetic spectrum. The density of quasars peaks during cosmic noon. When we survey nearby space, looking at galaxies relatively close to us in distance and time, quasars are rare. Most supermassive black holes are quiet dormant with little gas to feed on. But when we look back to cosmic noon, quasars are everywhere. This tells us that conditions during that era were fundamentally different. Galaxies had abundant gas. Mergers were more common. Black holes had fuel to grow rapidly. One of the most important surveys revealing cosmic noon was GOODS, the Great Observatories, Origins Deep Survey. This project combined data from multiple telescopes, Hubble and optical and near-infrared Spitzer, in infrared Chandra, in X-rays, and ground-based telescopes across many wavelengths. GOODS targeted 2 relatively small patches of sky, but observed them with unprecedented depth and breadth of wavelength coverage. What GOODS revealed was thousands of galaxies at various distances, and therefore various epochs. By measuring each galaxy's redshift, how much its light has been stretched by the universe's expansion, astronomers determined how far away each galaxy is, and therefore how long ago we're seeing it. Then they measured each galaxy's star formation rate by observing ultraviolet light from hot young stars and infrared light from dust heated by star formation. The result was a cosmic timeline. Plot star formation rate versus cosmic age for thousands of galaxies, and a clear pattern emerges. In the very early universe, galaxies were just forming, and star formation was ramping up. By cosmic noon, star formation peaked. After cosmic noon, it declined steadily to the low rates we see today. The universe has a history, a narrative arc, and we can see it by observing galaxies at different distances. This is where the story becomes truly magical. We're not theorizing about galactic evolution based on indirect evidence. We're watching it happen by looking at galaxies 13 billion light years away. We see them as they were when the universe was very young. Look at galaxies 10 billion light years away, and we see cosmic noon. Look at galaxies a few billion light years away, and we see the decline. Look nearby, and we see mature galaxies like the Milky Way. Each observation is a snapshot from a different moment in cosmic history. And when we assemble all these snapshots, we reconstruct the entire story. But why did cosmic noon happen when it did? Why did star formation peak at that particular era? The answer involves dark matter, the invisible substance that makes up about 85% of all matter in the universe. Dark matter doesn't interact with light, so we can't see it directly, but it interacts through gravity, and it's gravity that shapes the universe's large-scale structure. Shortly after the Big Bang, dark matter began clumping under its own gravity, forming vast halos. Normal matter, the gas that would eventually form stars, fell into these dark matter halos. The deepest wells of dark matter attracted the most gas. By cosmic noon, these dark matter halos had grown large enough to have accumulated substantial amounts of gas, but not so large that their gas had been heated to temperatures too high for star formation. It was a Goldilocks era. Halos were just the right size to efficiently form stars. Gas was abundant. Galaxies were actively merging, funneling gas toward their centers. Everything aligned for maximal star formation. After cosmic noon, several factors contributed to the decline. As the universe continued expanding, gas became more dispersed and harder for galaxies to accrete. Many galaxies consumed or expelled their gas through star formation and galactic winds. The largest dark matter halos grew so massive that gas falling into them was heated to millions of degrees, too hot to collapse and form stars. Supermassive black holes, having grown large during the quasar era, now generated enough energy to blow gas out of their galaxies entirely, a feedback process that shut down star formation. There's also a phenomenon called downsizing. Massive galaxies formed stars early and quickly shut down. By cosmic noon, the most massive galaxies were already transitioning from active star formers to passive systems with little ongoing star formation. Less massive galaxies continued forming stars longer. Today, the most massive galaxies are red and dead, filled with old red stars, forming almost no new stars. Smaller galaxies, like the Milky Way, continue forming stars, though at much lower rates than during cosmic noon. This downsizing effect emerged from telescope surveys that meticulously measured galaxy properties across cosmic time. By comparing massive galaxies at different epochs, astronomers discovered that the most massive systems shut down, first contradicting naive expectations that larger systems would take longer to form. The universe assembled its structure in a top-heavy fashion. What makes all of this truly remarkable is that every piece of evidence comes from looking backward through time. We're not inferring evolution from fossils or geological layers. We're directly observing galaxies at different stages of cosmic history. A galaxy 10 billion light years away shows us cosmic noon directly. We're capturing photons that left that galaxy when the universe was at its peak activity. The fact that we can do this, that the finite speed of light preserves cosmic history for our observation, is extraordinary. Before cosmic noon, there was an even earlier era, the cosmic dawn, when the very first stars and galaxies formed, when the universe transitioned from darkness to light, when neutral hydrogen was ionized by the first generation of stars. This is the frontier of observational astronomy, and it's where the James Webb Space Telescope is currently revolutionizing our understanding, discovering galaxies that, according to previous theories, shouldn't exist. But that story, the story of cosmic dawn and the first galaxies, is where everything gets really interesting. The James Webb Space Telescope launched on Christmas Day 2021, and after a 6-month commissioning period filled with nail-biting tension as its mirrors unfolded and aligned, it began observing the universe in the summer of 2022. Within weeks, it started sending back images that made astronomers question everything they thought they knew about early galaxy formation. One of Webb's earliest deep field images revealed a galaxy that astronomers cataloged as Glass Z13. The Z13 refers to its redshift, a measure of how much the universe has expanded since the light left that galaxy. A redshift of 13 corresponds to a distance of roughly 13.5 billion light years. The light we're seeing from Glass Z13 left that galaxy only about 300 million years after the Big Bang, when the universe was barely 2% of its current age. Now, 300 million years might sound like a long time. It is by human standards, but by cosmic standards, it's practically instantaneous. Remember that galaxies like the Milky Way took billions of years to assemble into their current forms. Theoretical models of galaxy formation developed over decades and refined through countless simulations predicted that the first galaxies should be small, dim, chaotic systems. They should be struggling to pull themselves together from the primordial gas. They should look nothing like mature galaxies. Glass Z13 doesn't follow the script. It's not small. It's not dim. It's surprisingly large and luminous. And it's not alone. Webb has discovered dozens of galaxies in this earliest epoch, and many of them are far more massive and organized than they have any right to be. Some show disk structures. Others have spiral features. These are supposed to take billions of years to develop, not a few 100 million. It's like expecting to see a 6-month-old infant crawling for the first time and instead finding them driving a truck. The universe apparently got very good at building galaxies very quickly, and we're only now discovering this because we finally have a telescope powerful enough to look that far back in time. One of the most shocking discoveries is how chemically enriched some of these early galaxies already are. When Webb analyzes the light from these distant galaxies using spectroscopy, breaking the light into its component wavelengths, it detects absorption and emission lines from elements like oxygen, carbon, and nitrogen. These heavy elements weren't present in the primordial universe. They can only be created through nuclear fusion in stars and dispersed through supernova explosions. The presence of these elements in galaxies only 300 to 500 million years after the Big Bang means that entire generations of stars must have already lived and died. The very first stars Population 3, stars made of pure hydrogen and helium, must have formed, lived out their brief lives, and exploded as supernovae within the first few 100 million years. Then, second-generation stars formed from the enriched gas. All of this happened on timescales that models suggested should be impossible. Population 3, stars have never been directly observed. They should have been massive, perhaps 100 to 1,000 times the mass of the Sun, burning incredibly hot and bright, but dying within just a few million years. Their explosions would have been spectacular, seeding the early universe with the first heavy elements. Webb might eventually detect the signature of these first stars, either directly by catching one in the act of exploding, or indirectly through their effects on surrounding gas. The rapid appearance of organized galactic structures also challenges our understanding. Previous models suggested that early galaxies should be irregular and clumpy, only gradually developing rotation and structure over hundreds of millions to billions of years. Yet Webb is detecting what appear to be disk galaxies and even spiral structures at redshifts beyond 10, corresponding to less than 500 million years after the Big Bang. These galaxies appear to have gotten their act together remarkably quickly. Several explanations are being proposed. Perhaps dark matter, halos, formed earlier and more efficiently than previously thought, providing gravitational wells that could rapidly accumulate gas and form stars. Perhaps the first stars were more massive than assumed, living and dying more quickly, enriching their environments faster. Perhaps feedback processes, the ways that supernovae and stellar winds regulate star formation, operated differently in the dense early universe. Or perhaps our entire timeline for galaxy formation needs revision. Webb's discoveries are forcing theorists back to their simulations. The universe has spoken through its light, and the message is clear: galaxy formation happened faster and more efficiently in the early universe than we thought possible. Our models need to catch up with reality. Another crucial era Webb is investigating is the epoch of Rayonization, which occurred roughly between 150 million and 1 billion years after the Big Bang. Before this epoch, the universe was dark and filled with neutral hydrogen, atoms with their electrons still attached. The very first stars and galaxies then formed, and their ultraviolet radiation began ionizing the surrounding hydrogen-stripping electrons from atoms. This ionization didn't happen all at once. It started in bubbles around the first galaxies. These bubbles expanded as more stars formed, gradually overlapping and merging. Eventually, the entire universe became ionized. The hydrogen gas that fills intergalactic space was stripped of its electrons and remains ionized to this day. Webb is detecting galaxies throughout this epoch, allowing astronomers to map how reionization progressed. By analyzing how much neutral hydrogen lies between us and these early galaxies, observed as absorption of specific wavelengths in their spectra, astronomers can determine what fraction of the universe was ionized at different times. The picture emerging is that reionization was a complex, patchy process, not a smooth transition. What makes all of this even more remarkable is the technology required to see it. These extremely distant galaxies have had their light stretched by cosmic expansion to wavelengths far into the infrared. Wavelengths that Hubble couldn't efficiently observe. Webb was specifically designed as an infrared telescope, cooled to 40 degrees above absolute zero, with a mirror optimized for infrared light. Without Webb, these galaxies would remain invisible, and our understanding of early cosmic history would remain based on extrapolation and theory rather than direct observation. Every photon Webb detects from these early galaxies has been traveling for over 13 billion years. It left its source when the universe was young and small, traveled through expanding space that stretched its wavelength, navigated around clusters of galaxies that gravitationally lensed it, and finally arrived at Webb's mirror. Each photon is a messenger from an era we can never visit, carrying information encoded in its wavelength and energy about conditions in the early universe. The galaxies we're seeing might look completely different now. They've had 13 billion years to evolve since the light we observe departed. They've likely merged with other galaxies, formed trillions more stars, developed supermassive black holes at their centers, and potentially joined massive galaxy clusters. Or they might have been destroyed, torn apart by tidal interactions their stars scattered across space. We won't know for 13 billion years, the time it would take light from their current state to reach us. For now, Webb continues pushing the frontier, detecting galaxies at higher and higher redshifts, each one breaking the previous record, each one revealing that the early universe was far more active and complex than our theories predicted. Somewhere in Webb's data might be a galaxy from the very edge of the observable universe, showing us light from just 100 million years after the Big Bang. The search continues, and with each discovery, our timeline of cosmic history gets rewritten. But even Webb has limits. There's a fundamental barrier beyond which no optical or infrared telescope can see, no matter how powerful. And that barrier, that ultimate curtain separating observation from theory, is where our journey through cosmic history reaches its end. There's a wall at the edge of observable cosmic history, not a physical wall, but an epoch before which the universe itself prevents us from seeing further back using light. That wall is the cosmic microwave background, and it represents the oldest light in the universe, the first light that could freely travel through space without being immediately absorbed. To understand the CMB, we need to rewind to the universe's first few 100,000 years. Immediately after the Big Bang, the universe was extraordinarily hot and dense, a plasma of protons, electrons, and photons all smashed together at temperatures of billions of degrees. In this state, matter and light were tightly coupled. Photons couldn't travel more than a tiny distance before scattering off a free electron. The universe was opaque, like a thick fog where you can't see more than a few feet ahead. As the universe expanded, it cooled. By about 380,000 years after the Big Bang, the temperature had dropped to roughly 3,000 degrees Kelvin, still incredibly hot by our standards, but cool enough for a crucial transition. At this temperature, electrons and protons combined to form neutral hydrogen atoms. This process is called recombination, and it fundamentally changed the nature of the universe. Once atoms formed, photons were suddenly free to travel. With electrons now bound into atoms rather than floating freely, there was nothing for the photons to scatter off. The universe became transparent, for the first time, light that was released at that moment has been traveling through space ever since, stretched by cosmic expansion from visible light into microwaves. That light fills the entire sky today as the cosmic microwave background. It comes from every direction uniform to about 1 part in 100,000 dollars with a temperature of 2.725 Kelvin, just 2.725 degrees above absolute zero. This radiation has been traveling for 13.8 billion years, and every telescope that observes it is seeing the universe as it was 380,000 years after the Big Bang. The CMB is remarkable for several reasons. First, it's the ultimate confirmation of the Big Bang theory. If the universe had always existed in more or less its current state, there would be no such background radiation. The CMB's existence and properties match predictions made by Big Bang cosmology with extraordinary precision. Second, tiny variations in the CMB's temperature contain a wealth of information about the universe. These variations, about 0.001 degrees across different patches of sky, represent density fluctuations in the primordial universe. Regions that were slightly denser than average appear slightly warmer. Regions that were slightly less dense appear slightly cooler. These fluctuations are the seeds from which all cosmic structure grew. Over billions of years, gravity amplified these tiny density differences, turning them into galaxy clusters and vast cosmic voids. 3 space missions have mapped the CMB in increasing detail. COBE, launched in 1989, made the first full sky maps and detected the temperature variations. WMAP, launched in 2001, operated for 9 years and produced far more detailed maps. Planck, launched in 2009, represented the ultimate precision, mapping the CMB to the limits of what's physically possible with current technology. From these maps, cosmologists extract fundamental parameters about the universe. The patterns of temperature fluctuations, analyzed through spherical harmonics, a mathematical technique for decomposing patterns on a sphere, reveal acoustic oscillations in the primordial plasma. Before recombination, pressure waves propagated through the hot plasma like sound waves. These waves left an imprint on the CMB that we can measure today. The positions and heights of peaks in the CMB power spectrum, a graph showing how much variation exists at different angular scales, depend on cosmic parameters like the universe's total density, the proportion of normal matter versus dark matter, the amount of dark energy, and the geometry of space itself. By fitting theoretical models to the observed power spectrum, cosmologists determine these parameters with remarkable precision. From the CMB, we know that the universe is flat. Its overall geometry is Euclidean, not curved like a sphere or saddle. We know it's 13.8 billion years old, with an uncertainty of less than 1%. We know that normal matter, the stuff of atoms and molecules, makes up only about 5% of the total energy density. Dark matter contributes about 27%, and dark energy accounts for the remaining 68%. The CMB also reveals something profound about causality and inflation. Different patches of the sky, separated by large angles, couldn't have been in causal contact. Light wouldn't have had time to travel between them in only 380,000 years. Yet these patches have the same temperature to extraordinary precision. How did they know to be the same temperature if they couldn't communicate? The answer likely involves inflation, a brief period of exponential expansion in the first fraction of a second. After the Big Bang, that stretched a tiny, causally connected region into something vastly larger than the observable universe. But that's venturing into realms where direct observation gives way to theoretical extrapolation. The CMB represents an absolute barrier for telescopes observing electromagnetic radiation. Before recombination, the universe was opaque. Any light from that era scattered countless times and carries no useful information about its sources. We cannot see before the CMB using visible light infrared radio waves or any other form of electromagnetic radiation. The first 380,000 years of cosmic history remain hidden behind this curtain. However, and this is where it gets interesting, electromagnetic radiation isn't the only messenger from the early universe. Neutrinos, nearly massless particles that barely interact with matter, decoupled from the rest of the universe when it was only 1 second old. There should be a cosmic neutrino background analogous to the CMB, but from an even earlier epoch. Unfortunately, these neutrinos have been stretched to such low energies by cosmic expansion that detecting them with current technology is essentially impossible. Future neutrino detectors might eventually observe them, pushing our observational window back to 1 second after the Big Bang. Even more exotic are gravitational waves, ripples in space-time itself. Primordial gravitational waves, if they exist, would have been generated during the inflationary epoch in the first fraction of a second after the Big Bang. These waves would have left a subtle imprint on the CMB's polarization pattern, a signature called B modes. Several experiments are searching for this signal, though contamination from our galaxy's magnetic fields and dust makes detection extremely challenging. If primordial B modes are detected, it would open a window to the universe's first instance, far earlier than anything observable with light. For now, the CMB remains the oldest light we can observe, the ultimate curtain behind which the universe's earliest moments are hidden from direct view. It's fitting in a way. The CMB represents the moment when light first traveled freely, when the universe became transparent, when observation became possible. Everything before that moment exists in a realm accessible only through theory, indirect evidence, and mathematical extrapolation. But what the CMB shows us is already extraordinary. We're seeing the universe as it was 380,000 years after the Big Bang, capturing photons that have been traveling for 13.8 billion years. These photons have journeyed across an expanding universe, their wavelengths stretched by a factor of about 1/100, arriving at our detectors as faint microwave radiation that tells us about the seeds of everything that would eventually form: galaxies, stars, planets, and ultimately us. Standing on Earth today, we can point a telescope in any direction and trace cosmic history backward through time. Nearby stars show us the past few years or decades. Distant galaxies reveal cosmic noon billions of years ago. The most distant galaxies Webb can detect show us the universe's first few 100 million years. And the CMB shows us the moment when light itself was born into the universe, free to travel and carry information across space and time. We've reached the limit of what light can show us, but the journey has revealed almost the entire history of the cosmos, frozen in photons that have been traveling to reach us since before the Earth, the Sun, or even the Milky Way existed in their current forms. The discoveries made by looking backward through time, have fundamentally transformed our understanding of the universe. And those discoveries, from cosmic expansion to dark energy to the unexpected complexity of early galaxies, are what we'll explore next. In 1929, Edwin Hubble was working at the Mount Wilson Observatory in California, home to what was then the world's largest telescope, a 100-inch reflector perched on a mountain above Los Angeles. Hubble was doing something that required extraordinary patience, measuring the distances to galaxies far beyond our own Milky Way. Distance measurement in astronomy is notoriously difficult. You can't just point a telescope at a galaxy and read off how far away it is. You need what astronomers call a standard candle, an object whose intrinsic brightness you know. By comparing how bright it appears to how bright it actually is, you can calculate distance. It's like seeing a 100-watt light bulb in the distance. If you know it's a 100-watt bulb, you can figure out how far away it is by measuring how dim it looks. Hubble's standard candles were Cepheid variable stars, stars that pulsate regularly, growing brighter and dimmer over periods of days to months. In 1912, Henrietta Leavitt had discovered something remarkable about Cepheids. Their pulsation period is directly related to their intrinsic luminosity. A Cepheid that pulsates over 50 days is intrinsically brighter than one that pulsates over 5 days. This relationship turned Cepheids into cosmic measuring sticks. Hubble painstakingly identified Cepheids in distant galaxies, measured their periods, determined their distances, and compiled a catalog. But he didn't stop there. He also measured something else, the velocities at which these galaxies were moving. He did this through spectroscopy, analyzing how the galaxy's light was shifted toward the red end of the spectrum. Redshift indicating motion away from us. When Hubble plotted distance versus velocity for the galaxies in his catalog, a pattern emerged that would change cosmology forever. The farther away a galaxy was, the faster it was moving away from us. Not just slightly faster, proportionally faster. Double the distance, double the recession velocity. Triple the distance, triple the velocity. The relationship was linear and undeniable. There was only one explanation that made sense: the universe itself was expanding. Space between galaxies was growing, carrying galaxies apart from each other, like dots on the surface of an inflating balloon. If you draw dots on a deflated balloon and then blow it up, every dot moves away from every other dot, not because the dots are moving through the balloon's surface, but because the surface itself is stretching. This wasn't a completely unprecedented idea. In 1927, 2 years before Hubble's publication, a Belgian priest and physicist named Georges Lemaitre had proposed, based on Einstein's equations of general relativity, that the universe should be expanding. But Lemaitre's work, published in a relatively obscure Belgian journal, had gone largely unnoticed. Hubble's observational evidence, actual measurements from actual galaxies, provided the proof that the universe was indeed expanding. The implications were staggering. If the universe is expanding now, then running time backward means it was smaller in the past, much smaller. Keep rewinding, and you reach a point where all the matter and energy in the universe was compressed into an incredibly hot, dense state. This was the birth of the Big Bang Theory. The idea that the universe had a definite beginning roughly 13.8 billion years ago. Before Hubble, the prevailing view among many cosmologists was that the universe was eternal and unchanging, what's called the steady state model. Hubble's discovery demolished this view. The universe had a history, it had an origin, it was dynamic, not static. This single discovery, made possible by looking backward through time at distant galaxies, fundamentally transformed our understanding of cosmic history. There's a delicious irony here. The Hubble constant, the rate of cosmic expansion, has been the subject of intense controversy for decades. Different measurement methods give slightly different values, and reconciling them remains one of cosmology's outstanding problems. Hubble's original value was off by a factor of 7 because of errors in the Cepheid distance scale. But despite these uncertainties, the basic discovery remains rock solid. The universe is expanding, and we discovered this by observing galaxies from millions of years ago through telescopes. Think about it this way. When you blow up a balloon, dots on the surface move apart. They're not traveling through space. Space itself is expanding. That's exactly what's happening to galaxies. And we discovered this not through theory alone, but by capturing photons that left distant galaxies millions of years ago, and measuring how their wavelengths had been stretched by cosmic expansion during their long journey to our instruments. But here's the thing. If the universe is expanding, and if gravity is pulling everything together, then logically, the expansion should be slowing down, right? Gravity should be acting as a brake, gradually decelerating the expansion. Eventually, maybe gravity might even reverse the expansion and pull everything back together in a big crunch. That's what every cosmologist expected to find when they set out to measure how much the expansion was slowing down. What they actually discovered was far stranger. By the 1990s, telescope technology had advanced enormously since Hubble's time. Astronomers could now detect supernovae in galaxies billions of light years away, far more distant than anything Hubble could observe. Two independent teams set out to measure cosmic deceleration by observing type Ia supernovae at various distances. Type Ia supernovae are almost perfect standard candles. They occur when a white dwarf star in a binary system accumulates matter from its companion until it reaches a critical mass, about 1.4 times the mass of the Sun. At this threshold, called the Chandrasekhar limit, the white dwarf can no longer support itself against gravity. It collapses catastrophically, triggering a thermonuclear explosion that destroys the entire star. Because this explosion always happens at the same mass threshold, type Ia supernovae always release roughly the same amount of energy. They all reach approximately the same peak brightness. This makes them ideal for measuring cosmic distances. Find a type Ia supernova in a distant galaxy, measure how bright it appears, compare that to how bright it should be, and you can calculate its distance. Measure its redshift, and you know its velocity. Do this for dozens of supernovae at various distances, and you can map out the expansion history of the universe. The Supernova Cosmology project and the High Z supernova search team spent years hunting for distant supernovae. They developed automated systems to rapidly compare images of the same patches of sky, identifying new points of light that appeared where nothing existed before. When they found a supernova, they immediately alerted larger telescopes to obtain detailed spectra and light curves. In 1998, both teams independently announced their results, and the results were shocking. The distant supernovae were dimmer than expected, significantly dimmer. This meant they were farther away than they should be, based on their redshifts, assuming a steadily expanding or decelerating universe. There was only one explanation. The expansion of the universe wasn't slowing down, it was speeding up. The universe's expansion had been accelerating for the past several billion years. At first, nobody believed it. The teams checked their instruments. They checked their analysis. They looked for sources of error. Perhaps dust in the distant galaxies was dimming the supernovae. Perhaps distant supernovae were intrinsically different from nearby ones. But every check confirmed the result. The universe's expansion was accelerating. This discovery required introducing something completely unexpected into cosmology: dark energy. Whatever dark energy is, and we genuinely don't know, it makes up roughly 68% of the universe's total energy density, and it has the bizarre property of causing space itself to expand faster over time. It's like anti-gravity, but operating on cosmic scales. The discovery earned the 1998 Nobel Prize in Physics, but it also humbled the entire field of cosmology. We thought we understood the universe's basic composition. Turns out we had missed the largest component, something that makes up more than 2/3 of everything, and we have almost no idea what it is. Several explanations have been proposed. Einstein's equations actually allow for a cosmological constant, a property of space itself that causes expansion. Einstein originally introduced this constant to keep the universe static before Hubble's discovery, then called it his biggest blunder when expansion was discovered. But maybe it wasn't a blunder after all. Perhaps the cosmological constant, representing the energy of empty space itself, or vacuum energy, is real and causing acceleration. Alternative theories suggest dark energy might be a new field or force we haven't discovered yet. Others propose modifications to general relativity itself. Whatever the explanation, the observational fact remains by observing supernovae. From billions of years ago, we discovered that the universe's expansion is accelerating. This has profound implications for cosmic fate. If acceleration continues, the universe will expand forever, growing ever more diffuse and cold. Galaxies outside our local group will eventually recede so fast that their light can never reach us. The night sky will gradually empty as galaxies disappear beyond the cosmic horizon. Trillions of years from now, any observers in the Milky Way will see only their own galaxy in an otherwise empty sky, with no evidence that other galaxies ever existed. But here's what makes this story so remarkable. Both Hubble's discovery of expansion and the 1998 team's discovery of acceleration came from observing the past through telescopes. Hubble looked at galaxies from millions of years ago. The supernova teams looked at explosions from billions of years ago. By assembling observations from different distances, different times in cosmic history, they reconstructed the expansion history of the universe. This is astronomy's unique power. We are not limited to observing the present. We can directly observe the past, see how things were billions of years ago, and trace how the universe has evolved. Dark energy dominates the universe today, but observations of the cosmic microwave background show it didn't significantly affect the early universe. By looking back through time, we can watch dark energy's influence grow. Now, dark energy is mysterious. We don't know what it is, but at least we can observe its effects. The accelerating expansion of space itself. There's something else in the universe that's even more abundant than dark energy, and we can't see it at all. We can only infer its existence through gravity, and this discovery too came from looking backward through time with telescopes. In the 1970s, astronomer Vera Rubin was doing something that seemed straightforward, measuring how fast stars orbit in spiral galaxies by observing spectral lines from stars at various distances from galactic centers and measuring their Doppler shifts. She could determine their orbital velocities. What she found made no sense. In our solar system, planets farther from the Sun orbit more slowly. Neptune plods along while Mercury races around. This is basic orbital mechanics. The farther you are from the central mass, the weaker its gravitational pull, the slower your orbit. Galaxies should work the same way. Stars near the galactic center should orbit quickly, while stars in the outer regions should orbit slowly. But that's not what Rubin observed. Stars in the outer reaches of galaxies were moving just as fast as stars closer in. In some cases, orbital velocity stayed constant or even increased with distance. This was completely unexpected. These outer stars were moving so fast they should fly off into intergalactic space. The visible matter in the galaxy simply didn't have enough gravity to hold them in orbit. There was only one possible explanation. Galaxies must contain far more mass than we can see. Invisible matter, dark matter, must be distributed throughout and around galaxies, providing the gravitational glue that keeps everything together. Rubin's rotation curves suggested that dark matter outweighs visible matter by factors of 5 or 10 to 1. This discovery was revolutionary and deeply unsettling. It meant that the star's gas planets and everything else we can observe with telescopes represent only about 15% of the total matter in the universe. The remaining 85% is completely invisible. It doesn't emit, absorb, or reflect light at any wavelength. We know it exists only through its gravitational effects. Hubble and other telescopes provided another line of evidence through gravitational lensing. Einstein's general relativity predicts that mass bends space-time, and light follows the curvature of space-time. When light from a distant galaxy passes near a massive cluster of galaxies in the foreground, the cluster's gravity bends the light's path. From our perspective, the background galaxy appears distorted, stretched into arcs, or even multiple images. By carefully analyzing these distortions, astronomers can map the distribution of mass in the foreground cluster, and what they find is that the mass distribution extends far beyond the visible galaxies. Dark matter halos surround galaxy clusters, containing far more mass than all the cluster's stars and gas combined. These lensing observations are particularly powerful because they're measuring mass directly through its gravitational effects, without any assumptions about what that mass is made of or whether it emits light. The distortions tell us where the mass is, and overwhelmingly, most of it is invisible. One of the most dramatic examples is the Bullet Cluster, two galaxy clusters that collided and passed through each other. When astronomers mapped the mass distribution using gravitational lensing, they found something remarkable. The dark matter, halos, passed through each other with minimal interaction, while the hot gas in both clusters collided and was left behind. This provides direct evidence that dark matter doesn't interact with normal matter, or even with itself except through gravity. So, what is dark matter? We don't know. Leading candidates include WIMPs, weakly interacting massive particles, hypothetical particles that barely interact with normal matter, or axions, even more exotic particles predicted by certain theories. Dozens of experiments worldwide are searching for these particles, trying to detect them directly or produce them in particle accelerators. So far, no confirmed detections. Here's what's genuinely humbling about modern cosmology. We've mapped the universe's composition with precision. Normal matter, atoms, molecules, everything in the periodic table makes up about 5% of total energy density. Dark matter contributes about 27%. Dark energy accounts for about 68%. We understand in detail only the 5%. The remaining 95% is mysterious. It's like buying a TV and only understanding how the remote control works. You can change channels and adjust volume, but the actual mechanism that creates the picture, complete mystery. Except in this case, the TV is the universe, and we've only figured out 5% of how it operates. Yet even this humbling realization came from telescopes looking backward through time. Galaxy rotation curves show us how dark matter was distributed millions of years ago. Gravitational lensing reveals dark matter's distribution across billions of years of cosmic history. Observations of the cosmic microwave background show us dark matter's influence 13.8 billion years ago when it formed the gravitational seeds that grew into today's galaxies. Dark matter and dark energy dominate the universe, yet we discovered them indirectly by observing light from the past. Photons from distant galaxies gravitationally lensed by invisible matter traveling billions of years to reach us, revealing that most of the universe is made of things we can't see. But telescopes don't just reveal the universe's composition and history. They're also beginning to answer one of humanity's oldest questions. Are we alone? Before 1995, we knew of exactly 9 planets, the ones orbiting our sun. We suspected other stars might have planets, but we had no proof. Then in 1995, Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, the first confirmed planet orbiting a sun-like star. The discovery was shocking, not because planets existed, but because this particular planet was utterly bizarre. It was a gas giant like Jupiter, but orbiting so close to its star that it completed an orbit every 4.2 days. Its surface temperature was over 1,000 degrees Celsius. Nothing like this existed in our solar system. This hot Jupiter opened the floodgates. Astronomers realized planets came in configurations we'd never imagined. Today we've confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. We've found planets orbiting binary stars, planets with years lasting just hours, super Earths and mini Neptunes with no analog in our solar system, free-floating planets ejected from their star systems entirely. The diversity is staggering. 3 main techniques detect exoplanets, each relying on observing the past. The transit method watches for tiny dips in a star's brightness when a planet passes in front of it. The Kepler Space Telescope used this method to discover thousands of planets by staring at 150,000 stars for 4 years, detecting the periodic brightness changes that indicate orbiting planets. Every transit Kepler observed happened years or decades before, depending on the star's distance. The radial velocity method detects the tiny wobble a planet induces in its host star as both orbit their common center of mass. By measuring Doppler shifts in the star's spectrum, astronomers can infer the planet's presence. This was the method used to discover 51 Pegasi b, and it remains powerful for detecting massive planets in close orbits. Direct imaging, actually photographing planets, is extraordinarily difficult because planets are millions of times fainter than their stars. It's like trying to see a firefly next to a searchlight. But advanced techniques using coronagraphs to block starlight and adaptive optics to sharpen images have successfully imaged a few dozen planets, typically young hot planets orbiting far from their stars. The James Webb Space Telescope is now doing something even more remarkable, analyzing exoplanet atmospheres. Through transit spectroscopy, when a planet transits, some starlight filters through the planet's atmosphere. Molecules in that atmosphere absorb specific wavelengths. By comparing the star's spectrum during transit versus outside transit, astronomers can identify which molecules are present. Webb has detected water vapor, carbon dioxide, methane, and other molecules in several exoplanet atmospheres. These are hot Jupiters, gas giants, orbiting close to their stars, definitely not habitable. But the same techniques will eventually be applied to smaller, cooler planets in their stars' habitable zones. The range of distances where liquid water could exist on a planet's surface. The search for biosignatures focuses on atmospheric combinations that would be difficult to maintain without life. On Earth, oxygen makes up 21% of our atmosphere, but it's chemically reactive and would disappear within a few million years if not constantly replenished by photosynthesis. Finding abundant oxygen in an exoplanet's atmosphere would be compelling evidence for life. Even more telling would be finding oxygen together with methane. These gases react with each other, so their simultaneous presence suggests ongoing production by biological processes. On Earth, oxygen comes from plants and algae, while methane comes from bacteria and decomposition. Several potentially habitable planets are already known. The TRAPPIST-1 system contains 7 Earth-sized planets, 3 in the habitable zone just 40 light-years away. Proxima Centauri b orbits the closest star to our Sun, only 4.2 light-years distant. These planets are prime targets for atmospheric characterization. But here's the temporal twist that makes this search profound. If we detect biosignatures on a planet 100 light-years away, we're seeing evidence of life from 100 years ago. Those organisms might have evolved significantly. They might have died out. Or if they're intelligent and technological, they might have built civilizations we can't yet detect. This is where SETI, the search for extraterrestrial intelligence, becomes relevant. Radio telescopes have been scanning the sky for artificial signals since the 1960s. Any detection would represent a message from the past. A signal from 1,000 light-years away would show us alien technology from 1,000 years ago, from when humans were building medieval castles and had no concept of radio waves. The Drake equation attempts to estimate how many communicating civilizations exist in our galaxy. One crucial factor is L, the average lifetime of a technological civilization. This matters because we can only detect civilizations that existed at the right time for their signals to be reaching us now. Civilizations that rose and fell millions of years ago remain invisible unless they left permanent artifacts. Communication across these distances becomes almost philosophical. Imagine we detect a signal from 1,000 light years away. We analyze it, decode it, perhaps learn about their science and culture. We send a reply. It takes 1,000 years to reach them. If they reply to our reply, we receive that response in the year 4025. This isn't conversation. It's corresponding across millennia. Think about the practical absurdity. Hi, aliens. We received your message from 1,000 years ago. How's it going? We'll check back in 2,000 years for your response. It's like having a ping time of 2,000 years. Worse than dial-up internet in 1995. Substantially worse. Yet this constraint makes the search even more profound. Any signal we detect is fundamentally historical. We're not learning about contemporary aliens. We're learning about their past. If they're 1,000 light years away, and we detect their first radio broadcasts by the time we hear them, they might have advanced to technologies we can't imagine, or destroyed themselves, or transcended biology entirely. The habitable zone around a star changes as that star evolves. Early in its life, the habitable zone is closer. As the star ages and brightens, the zone moves outward. A planet might be frozen for billions of years, then warm into habitability, then eventually become too hot. Telescopes observing these systems capture single snapshots from specific moments in planetary history. Future telescopes might directly image Earth-like planets around nearby stars. The proposed Habitable Worlds Observatory would photograph rocky planets in habitable zones and analyze their atmospheres for biosignatures. If it images a planet 30 light years away, showing signs of life, we're observing alien organisms from 30 years ago. Life forms that have lived, reproduced, evolved, and perhaps died in the decades since that light departed. The search for life through telescopes is fundamentally a search through time. Every observation captures the past. Every biosignature, if we find one, tells us life existed years, or decades, or centuries ago. We may discover that life is common in the universe, but we'll always be observing it in hindsight through the delayed messenger of light traveling across the cosmic void. The telescopes operating today are extraordinary, but they're just the beginning. A new generation of observatories is under construction or in planning stages, each designed to push deeper into cosmic history and reveal phenomena current instruments can barely glimpse. On the ground, the extremely large telescope is taking shape on Cerro Armazones in Chile's Atacama Desert. When completed in the late 2020s, it will have a primary mirror 39 meters across, larger than a tennis court, composed of 798 hexagonal segments. Each segment must be aligned with nanometer precision and continuously adjusted as the telescope moves and as temperature changes affect the structure. The ELT will collect about 15 times more light than any current optical telescope, allowing it to see objects 15 times fainter or probe 15 times deeper into cosmic history. The Giant Magellan Telescope and 30-meter telescope represent alternative approaches to extreme size. GMT uses 7 8.4-meter mirrors arranged in a flower pattern, effectively creating a 25-meter telescope. TMT, delayed by protests on Mauna Kea, would use 492 segments to form a 30-meter mirror. Together with ELT, these ground-based monsters will observe from different hemispheres, covering the entire sky with unprecedented power. Advanced adaptive optic systems on these telescopes will correct atmospheric distortion across wider fields than currently possible. Multi-conjugate adaptive optics corrects turbulence at multiple atmospheric layers, simultaneously allowing large patches of sky to be observed at near perfect resolution. These systems will make ground-based telescopes rival space observatories in image quality while collecting far more light. In space, the Nancy Grace Roman Space Telescope will launch in the mid-2020s with a field of view 100 times larger than Hubble's. This makes Roman perfect for surveys, mapping cosmic structure across billions of years, finding thousands of supernovae to trace dark energy's history, and conducting weak gravitational lensing surveys that map dark matter distribution across vast volumes of space and time. Roman will capture multiple epochs of cosmic history in single exposures, each galaxy revealing a different moment in the universe's evolution. Looking further ahead, the Habitable Worlds Observatory is planned for the 2040s, specifically designed to directly image Earth-like exoplanets and characterize their atmospheres. HWO would use a coronagraph or star shade to block starlight, allowing much fainter planets to be photographed. If successful, it could image dozens of potentially habitable worlds, analyze their atmospheres for biosignatures, and perhaps answer whether Earth-like life is common or rare in the cosmos. Every planet it images would be seen as it existed years or decades ago, a snapshot from the recent past of worlds that might harbor life. LISA, the Laser Interferometer Space Antenna, will detect gravitational waves from space. 3 spacecraft flying in a triangular formation, millions of kilometers apart, will measure gravitational waves at frequencies inaccessible to ground-based detectors like LIGO. LISA will observe supermassive black hole mergers from across cosmic history, potentially detecting the mergers of the first black holes that formed in the early universe. These observations would reveal events from billions of years ago through ripples in space-time itself. Beyond electromagnetic radiation, future detectors might observe the cosmic neutrino background, neutrinos that decoupled from the rest of the universe when it was only 1 second old. These neutrinos have been traveling freely ever since stretched to incredibly low energies by cosmic expansion. Detecting them would push observational cosmology back to just 1 second after the Big Bang, far earlier than the cosmic microwave background. Primordial gravitational waves from cosmic inflation would carry information from the universe's first fraction of a second. Multiple experiments are searching for the imprint these waves would leave on the CMB's polarization pattern. Detection would open a window to the inflationary epoch when the universe expanded exponentially in the first 10.32 seconds, setting the stage for everything that followed. These ambitious projects face significant challenges. Launch vehicles limit space telescope size. Webb required an extraordinary deployment sequence because it was too large to fit in any rocket fully assembled. SpaceX's Starship might enable much larger space telescopes if it becomes operational, potentially launching mirrors 10 or more meters across without folding. Funding remains a perpetual challenge. ELT costs roughly $1.3 billion. Webb costs nearly $10 billion over its development. Future space telescopes could cost even more. Governments must be convinced that scientific returns justify these investments, competing against other priorities. Light pollution increasingly threatens ground-based astronomy. Growing cities and satellite mega-constellations add unwanted light that contaminates observations. Future ground-based telescopes will need sophisticated algorithms to remove satellite trails, or must be built in ever more remote locations. Data volume from next-generation surveys will be staggering. The Vera C. Rubin Observatory will generate about 20 terabytes nightly. Processing this flood requires massive computing infrastructure and sophisticated algorithms, increasingly relying on machine learning to identify interesting phenomena in vast datasets. The challenge is developing AI systems that don't miss unexpected discoveries because they weren't trained to recognize them. Some revolutionary technologies remain on the horizon. Quantum sensors might achieve sensitivities impossible with classical detectors. Space-based interferometry could achieve angular resolution equivalent to telescopes thousands of kilometers across by combining light from multiple spacecraft flying in precise formations. A radio telescope on the lunar far side, shielded from Earth's interference, could observe wavelengths blocked by our ionosphere. But even as technology advances, the fundamental principle remains constant. Telescopes are time machines. Light's finite speed transforms every observation into historical documentation. The farther we look, the further back we see. Distance and time become inseparable. This has philosophical implications that resonate beyond astronomy. Our experience of the universe, beyond our immediate vicinity, is fundamentally historical. We never see distant objects as they are, only as they were. The present moment for distant locations is inaccessible to observation hidden beyond the horizon, created by light's travel time. Yet this constraint is also a gift. Because light takes time to travel, the past isn't lost. It's preserved in photons journeying through space. Ancient events remain accessible to observation. We can study cosmic history directly by intercepting light from various distances, assembling snapshots from different epochs into a coherent narrative of how the universe evolved. Every discovery we've discussed came from this capability. Hubble discovered cosmic expansion by observing galaxies from millions of years ago. The supernova teams discovered dark energy by observing explosions from billions of years ago. We mapped dark matter by analyzing lensing from across cosmic history. We found the earliest galaxies by capturing photons that traveled for over 13 billion years. The cosmic microwave background shows us the universe from 380,000 years after the Big Bang. We are carbon-based consciousness, assembled from atoms, forged in stars billions of years ago, using telescopes to observe light from our cosmic origins. We're matter, observing its own history, consciousness examining the process that created it. The story has no ending, because the universe continues sending messages. Light from distant galaxies is traveling toward us right now, carrying information about events happening billions of years ago that we'll observe in the future. The next time you look at the night sky, remember, you're not seeing the present, you're seeing history. Every photon entering your eye has traveled for years, centuries, or eons. You're standing in the present while simultaneously observing multiple moments from the past. That's the only superpower humans have, seeing through time. And telescopes are the greatest time machines we've ever built.